There is a place 3 feet above your head where warmth ceases to have meaning. Not the cold you know, not the bite of winter wind or the ache of bare fingers wrapped around a frozen railing. Something older, something the human body was never built to understand. Right now, beyond the thin membrane of atmosphere clinging to this spinning rock, the void between the stars sits at 2.7 degrees, above the coldest condition the laws of physics will ever permit. 2.7 Kelvin. Colder than liquid helium. Colder than any winter that has ever howled across any continent in the 4.5 billion year history of this world. And it stretches in every direction for distances your mind cannot hold. Not for millions of miles, not for billions, but for billions of light years. Each one a corridor of silence so deep that the very concept of temperature begins to dissolve. You think you know what cold means. You do not, and what the real answer reveals about the nature of this universe, about where warmth comes from and how little of it exists and how briefly it will last, is something that changes the way you see every star in the sky above you. If journeys like this one are why you are here, take a quiet moment and hit subscribe. It is a small thing that makes these long explorations possible, and it means more than you know. Now make yourself warm and comfortable, because by the time we are finished, the universe will look nothing like it did when you sat down. Are you ready? Let's begin. Ask anyone how cold space is, and they will answer without a moment's hesitation. Freezing, absolute zero, colder than anything on Earth. They will say it the way they might say, the sky is blue or water is wet, with the easy confidence of someone stating something so obvious it barely deserves the question. Space is dark, space is empty, space is lifeless. Of course it is cold. But that confident answer is wrong. Not slightly wrong, fundamentally wrong. The question itself contains a hidden assumption that most people never notice. A trap built into the way human beings experience the world. And the real answer is so much stranger and more unsettling than any number on any thermometer. Understanding why requires you to dismantle everything you think you know about temperature, about cold, and about the nature of emptiness itself. Because the universe does not work the way your body tells you it does. Not even close. If you are the kind of person who finds that idea thrilling rather than frightening, the kind of person who wants to follow a question all the way to the bottom, even when the bottom turns out to be deeper than you expected, then you are in the right place. And if you enjoy these journeys, do me a small favor. Hit subscribe, and if you feel like it, the like button too. It genuinely helps this channel continue to exist, and it lets me keep making these long, quiet explorations for you. Now, back to the cold. Here is the problem. When you say something is cold, you are describing a sensation. You are talking about heat leaving your body and entering the surrounding environment. Step outside on a January night in Minnesota and the air attacks you. Billions of molecules of nitrogen and oxygen slam into your skin every second. Each collision steals a tiny fraction of your body's heat. Your nerve endings register this energy loss and send a signal screaming up through your nervous system to your brain. Cold. That experience is so universal, so deeply wired into human biology, that we assume it describes a property of the environment itself. We say the air is cold. We say the water is cold. We say the metal railing is cold. But what we really mean is that those substances are conducting heat away from our bodies faster than our metabolism can replace it. Cold is not a thing. Cold is the absence of a thing. It is what happens when energy leaves. This distinction matters enormously because it exposes a flaw in how we frame the question about space. We ask how cold is space as though space were a substance with a measurable temperature, like asking how cold is the ocean, or how cold is the Arctic wind. But space is not a substance. The vacuum between the stars is not filled with cold stuff. It is filled with almost nothing at all. Now imagine something. Remove the air from around your body. Remove every molecule of gas, every particle of dust, every atom of matter for millions of miles in every direction. You are floating in the vacuum of deep space. Nothing touches your skin. No molecules collide with your body. No substance exists to steal your heat through the contact. So, what temperature is it out there? The answer is that the question barely makes sense. Temperature, in the way human beings experience it, requires matter. It is a measurement of how fast particles are moving. In a gas, temperature describes the average kinetic energy of molecules bouncing around in random directions. Hotter gas means faster molecules. Cooler gas means slower ones. When those molecules collide with your skin, the fast ones transfer more energy than the slow ones. That is why hot air feels hot and cold air feels cold. It is a story about motion and collision at the atomic level. A story that requires actors on a stage. In space, the stage is almost completely empty. A cubic centimeter of air at sea level on Earth contains roughly 25 billion molecules. That is a 25 followed by 18 zeros. Every breath you take pulls in this inconceivable swarm of particles, each one moving at hundreds of meters per second, each one capable of transferring energy to whatever it touches. Now consider a cubic centimeter of interstellar space. It might contain a single atom, maybe less. The density is so extraordinarily low that calling it a gas stretches the definition beyond recognition. You could not measure its temperature with any conventional thermometer because there is simply not enough matter present to transfer energy to the instrument in any detectable way. The thermometer would sit there in the void, surrounded by nothingness, and it would measure only itself. This is the first crack in the common understanding. Space is not cold the way a freezer is cold. A freezer is full of cold air, cold molecules pressing against everything inside, draining heat through direct contact. Space has almost nothing to press against you at all. If you placed a thermometer in deep space, far from any star or planet, it would not read the temperature of space. It would read its own temperature, and that temperature would depend entirely on what radiation the thermometer was absorbing and what radiation it was emitting. The instrument becomes the subject of its own measurement. It tells you about itself, not about the void surrounding it. Think about that for a moment. You send a thermometer into the emptiest place you can find, and instead of reporting on the emptiness, it reports on its own condition, like asking a mirror what the darkness looks like, and getting back only your own reflection. This is where our intuition fails us completely. On Earth, we live at the bottom of an ocean of air so thick and so omnipresent that we forget it is there. Every thermal experience you have ever had, every shiver, every sunburn, every warm bath, every frozen morning, has been mediated by matter, by molecules touching your skin, stealing your heat, or delivering theirs. You have never once in your life experienced temperature the way it works in space, because you have never once been without an atmosphere to translate the thermal world into something your body can understand. Space strips away that translator, and without it, the rules change completely. So if space is not cold in the way we normally mean, if there is no frozen air pressing against you, no icy wind stealing warmth from your skin, then what actually happens to heat out there? Where does it go? And how does an object floating in the void lose or gain warmth at all? To answer that, you need to know about the 3 ways heat moves from one place to another. Just 3. And once you understand them, the entire thermal strangeness of space clicks into place like a key turning in a lock. The first way is conduction. This is the simplest one. Place your hand flat on a metal countertop. Heat flows from your warm skin directly into the cooler metal through physical contact. The molecules in your hand vibrate, and that vibration passes into the molecules of the metal surface, one neighbor nudging the next like a chain of falling dominoes. This is why a metal spoon left in a hot pot burns your fingers. The heat traveled through the metal by conduction. It requires 2 things touching, and both things must be made of matter. Here is something most people never think about. Metal feels colder than wood at the same temperature. Touch a wooden table and a steel table, sitting side by side in the same room. The steel feels colder, but they are the exact same temperature. Your brain is lying to you. What you are actually feeling is not temperature at all. You are feeling the speed at which each material pulls heat out of your hand. Metal conducts heat faster, so your brain reads it as colder. Same temperature, different sensation. Your body is not a thermometer. It is an energy loss detector. In space, conduction is meaningless. There is nothing to touch. No surface, no substance. No matter to carry heat from one point to another through contact. You could float for 1 billion years and nothing would ever conduct heat away from your body because nothing would ever touch you. The second way heat moves is convection. Turn on a heater in your living room and watch what happens. Warm air rises to the ceiling. Cool air sinks to the floor. This circulation pattern moves heat through the room by physically carrying warm material from one place to another. Convection is what makes weather possible on Earth. It drives ocean currents. It carries heat from the equator toward the poles. It is the reason a breeze feels cool on a hot day, because moving air carries your body heat away faster than still air does. But convection needs a fluid to work. Air, water, something that can flow. In space, there is no fluid, no air to rise or fall, no currents to carry warmth from here to there. The void is perfectly still, perfectly empty, beyond anything you have ever experienced on Earth. Convection simply does not exist out there, so conduction needs contact. Gone. Convection needs fluid. Gone. That leaves only the third way, and this third way changes everything. Radiation. Every object with a temperature above absolute zero gives off electromagnetic radiation. Right now, as you listen to these words, your body is radiating infrared light. You cannot see it. You cannot feel it leaving. But it is streaming outward from your skin in every direction, carrying tiny packets of energy into the surrounding space. The walls around you are doing the same thing, radiating infrared light back towards you. The sun radiates visible light, ultraviolet light, infrared light, and energy across a wide band of the electromagnetic spectrum. Here is what makes radiation different from the other two. It does not need matter. It does not need contact. It does not need fluid. It travels through complete emptiness as naturally as a fish moves through water. Light from the sun crosses 93 million miles of perfect vacuum to reach your face. No molecules help it along the way. No substance carries it. It moves through nothingness at the speed of light, and it arrives with its energy intact. Radiation is the only way heat moves in the vacuum of space. The only way. And this single fact transforms how temperature works beyond Earth's atmosphere. It means that the thermal experience of any object in space is not determined by what surrounds it. It is determined by what shines on it. The void itself does nothing. It does not warm. It does not cool. It simply allows radiation to pass through without interference. Your temperature in space depends entirely on the balance between the radiation pouring in and the radiation streaming out. And this creates something terrifying. Thermal extremes separated not by miles or continents, but by inches. Picture a bolt on the outside of a spacecraft in orbit around Earth. The sun is shining. On one side of that bolt, the side facing the sun, solar radiation pours in at roughly 1,360 watts per square meter. That is like pressing a small space heater against every square meter of sunlit surface. The metal heats up. Without anything to moderate the input, the temperature on the sunlit side can climb past 120 degrees Celsius. Hot enough to boil water. Hot enough to cause severe burns on bare skin. Now look at the other side of that same bolt, the side facing away from the sun. It receives no direct solar radiation. It is radiating its own heat into the void as infrared photons, streaming energy outward into the darkness with nothing coming back. The temperature on that shadowed side can plunge to minus 170 degrees Celsius, cold enough to make steel crack, cold enough to freeze human tissue solid. One bolt, less than a centimeter of metal, a temperature difference of nearly 300 degrees from one side to the other. On Earth, this could never happen. Step from sunlight into shade on a summer afternoon, and the air temperature changes by maybe a degree or two. The atmosphere acts as a buffer. Wind carries warm air into cool shadows. Rising thermals lift heated air upward and pull cooler air down. The atmosphere is an enormous thermal blanket that redistributes energy and softens every extreme. It smooths things out. It keeps everything within a range your body can handle. In space, there is no blanket, no buffer, no smoothing. Radiation creates savage thermal cliffs across distances smaller than the width of your hand. One side of an object is scorching. The other side is frozen. There is no gentle gradient between them, no transition zone, just a hard line where sunlight ends and shadow begins, and the temperature drops off a cliff. This is what makes the thermal environment of space so alien. It is not that space is uniformly freezing. It is that space does not care about your temperature at all. It offers no protection, no insulation, no moderation. Whatever radiation hits you determines whether you bake or freeze, and both can happen to the same object at the same time. The cold of space is not an attack. Cold air on a winter night attacks you. It sends billions of molecules slamming into your skin, each one stealing heat. The wind accelerates the assault. The cold is aggressive, active, relentless. Space does none of that. Space is simply doing nothing. It offers no resistance, no warmth, no chill. It is thermally empty. Your body radiates heat into it because your body is warmer than the void. And nothing in the void replaces that lost energy unless a radiation source happens to be shining on you. The cold of space is not an assault. It is an abandonment. The universe simply turns its back and leaves you to your own thermal fate. You are not attacked by cold. You are forgotten by warmth. And this forgetting extends in every direction, at every scale, across distances so vast that the word distance starts to lose its meaning. From the width of a single bolt on a space station to the empty corridors between stars that stretch for trillions of miles, the same rule applies. Radiation is the only game in town. What shines on you is all that matters. And most of space, the overwhelming majority of it, sits in permanent shadow, where almost nothing shines at all. Science fiction has taught us something about space that is almost entirely wrong. You have seen it in movies a dozen times. An astronaut's helmet cracks, or an airlock opens without warning, and the person exposed to vacuum freezes instantly. Ice crystals form on their skin. Their body turns rigid and blue in seconds. The scene is dramatic. It is visually striking. And it is completely misleading about what actually happens. If you were suddenly exposed to the vacuum of space in sunlight, you would not freeze. You would overheat, at least on one side. The sun would pour radiation into your body at over 1300 watts per square meter with no atmosphere to soften the blow. Your skin would burn. Meanwhile, the side of your body facing away from the sun would begin losing heat through radiation alone, slowly, steadily, photon by photon streaming into the darkness. You would not flash freeze because there is no cold substance surrounding you to rip the heat away. There is only emptiness, and emptiness is patient. It takes what you give it, one infrared photon at a time, and offers nothing in return. The real danger of vacuum exposure is not freezing. It is the loss of air pressure. Your lungs would empty. The moisture on your tongue and in your eyes would begin to boil. Not because it is hot, but because the boiling point of water drops dramatically when pressure disappears. Consciousness would fade within about 15 seconds as oxygen left your blood. A death would follow within minutes, but not from cold. The cold would come later, much later, as your body slowly radiated its stored heat into the void over the course of hours. No dramatic ice, no instant freeze, just a quiet, invisible departure of warmth that no one would ever see. This is why astronauts wear spacesuits. And a spacesuit is not what most people think it is. It is not a warm coat for a cold environment. It is a complete life support system designed to solve a problem far more complicated than staying warm. The suit must maintain air pressure around the body. It must supply oxygen and remove carbon dioxide. It must manage moisture from sweat and breathing. And critically, it must handle heat, not just cold, but heat, because an astronaut working hard in a spacesuit generates a surprising amount of body warmth with nowhere for it to go. On Earth, when you exercise, you sweat, and the air evaporates that sweat, carrying heat away from your skin. In a sealed spacesuit, there is no breeze, no evaporation into open air. The heat builds. Without active cooling, an astronaut performing a spacewalk would cook inside their own suit long before cold became a concern. NASA's Extravehicular Mobility Unit solves this with a liquid cooling garment, a mesh of thin tubes worn against the skin through which chilled water circulates, pulling heat from the astronaut's body and carrying it to a sublimator that vents it into space as water vapor. The suit is fighting heat on the inside while managing radiation on the outside. Its outer layers are designed to reflect as much solar radiation as possible, which is why spacesuits are white. Dark surfaces absorb more radiation. Light surfaces reflect it. A black spacesuit in direct sunlight would become dangerously hot within minutes. The white surface bounces most of the solar energy away before it can be absorbed. Even so, the sunlit side of the suit runs warm, and the shadowed side runs cold, and the suit's internal systems must constantly adjust to keep the astronaut's body at a livable temperature no matter which direction they happen to be facing. Every 90 minutes, the International Space Station completes one full orbit around Earth. During that orbit, it passes from full sunlight into Earth's shadow and back again. The transition is not gradual. There is no long sunset, no slow dimming. One moment the sun is there, blazing at full intensity. The next moment the station crosses into the planet's shadow and the sun vanishes. Darkness falls in seconds. The thermal environment flips from baking to bleeding heat in the time it takes to draw a breath. During the sunlit portion of the orbit, the station's exterior surfaces facing the sun can reach over 150 degrees Celsius. During the shadow portion, those same surfaces can drop below minus 150. That is a 300-degree swing happening every 45 minutes, because each orbit spends roughly half its time in sunlight and half in shadow. No environment on Earth even approaches this kind of thermal violence. The hottest deserts and coldest poles are separated by thousands of miles and experience their extremes across different seasons. The space station experiences both extremes across a single orbit, separated by nothing more than the curved edge of Earth's shadow. Astronauts who have performed spacewalks describe something that words struggle to capture. You can feel the sun on your visor. Not warmth exactly, because the suit's layers prevent direct heat transfer, but a kind of pressure, an awareness that enormous energy is hitting you from one direction. Then you rotate, and the sun moves behind you, and suddenly you are facing nothing but black sky. And somewhere in your body, you register the absence. Not cold in the way you know cold, just the sense that something has stopped arriving. One astronaut described it as standing next to a bonfire on a freezing night. Turn toward the fire and you are warm. Turn away and the cold is immediate. Except in space, the bonfire is a nuclear furnace 93 million miles away. And the freezing night is not minus 20 or minus 40. It is minus 270. And there is no ground beneath your feet, no air around your body, no sound at all. Just you, sealed inside a pressurized fabric shell, hanging between a star and the void, with nothing but engineering standing between you and a thermal environment that would kill you in minutes from either direction. This is what thermal indifference really means. Space is not hostile the way a blizzard is hostile. A blizzard attacks you. Wind and cold and ice work together to strip heat from your body as fast as possible. Space does not attack. It does not do anything at all. It simply presents you with raw, unfiltered radiation on one side and absolute emptiness on the other, and lets physics sort out the consequences. There is no malice in it. There is no force working against you. There is just the absence of everything that has ever protected you, and the presence of a radiation source powerful enough to cook you if you face it wrong, and a void deep enough to drain you, dry if you face the other way. The danger is not that space is cold. The danger is that space has no opinion about your survival. It does not lean toward freezing you or burning you. It simply allows both to happen simultaneously, on the same body, in the same moment, separated by nothing more than which direction your chest happens to point. Your body becomes a boundary line between two thermal worlds that should never exist side by side, and yet do, everywhere, across every orbit, around every planet, near every star in the universe. And the astronaut is the easy case. The astronaut is close to a star, bathed in powerful solar radiation, orbiting a planet that reflects additional light and warmth. What happens when you move away from the star? What happens on a world with no atmosphere at all, where radiation rules without any competition, and the surface itself becomes the stage for thermal extremes that make orbital spacewalks look gentle by comparison? The moon has that answer, and it is not a comfortable one. The moon is the closest example we have of what radiation does to a surface when nothing stands in its way. No atmosphere, no air, not a single molecule of protective gas between the ground and the emptiness above. The moon is naked rock exposed directly to the universe, and the thermal story it tells is one of savage extremes that make Earth's worst weather look gentle. When the sun shines on the moon's equator during the lunar day, the surface heats to roughly 127 degrees Celsius. That is hotter than boiling water. hotter than the maximum setting on most kitchen ovens. The regolith, that fine grey powder covering the lunar surface, bakes under direct sunlight with nothing to soften the incoming energy. No clouds to scatter the light, no wind to carry heat from one region to another, no moisture to absorb and redistribute energy. Just raw solar radiation pouring into exposed rock at full intensity, hour after hour, for roughly 2 weeks straight. Because the moon rotates slowly, each spot on the equator spends about 14 Earth days in continuous sunlight, 14 days of uninterrupted baking. Then the sun sets, and what follows is not a cool evening. When that same patch of ground rotates into the 2-week lunar night, the surface temperature plunges to roughly minus 173 degrees Celsius. The ground that was hot enough to boil water now drops cold enough to freeze carbon dioxide into dry ice, cold enough to make most metals brittle, but cold enough to kill any living cell in minutes. The swing is approximately 300 degrees. 300 degrees on the same patch of ground, driven entirely by whether the sun happens to be shining on it or not. To feel the weight of that number, compare it to Earth. The most extreme deserts on our planet, places like the Sahara or Central Australia, experience temperature swings of perhaps 50 or 60 degrees between the hottest afternoon and the coldest pre-dawn hour. That is considered brutal. People die from those swings. Survival requires shelter, water, preparation. The moon's swings are 5 to 6 times more violent, and they happen with mechanical regularity every single lunar cycle across the entire surface, and have been happening for over 4 billion years. The difference is atmosphere. That is the entire explanation. Earth has one. The moon does not. Think about what atmosphere actually does for you. On a summer afternoon, you step from bright sunlight into the shade of a tree. The air temperature drops by maybe 1 or 2 degrees, maybe 3 if the shade is deep. The difference is so small you barely notice it. You might feel slightly cooler, but the air surrounding you in shadow is nearly the same temperature as the air in full sun, because the atmosphere mixes constantly. Wind carries warm air into shaded areas. Thermals lift heated air upward and pull cooler air down. The entire atmosphere behaves like an enormous stirring mechanism that blends temperatures together and prevents any one spot from becoming drastically hotter or colder than the spots around it. Now remove that atmosphere entirely. Remove the mixing. Remove the blending. Remove the thermal blanket. What you have left is the moon. And on the moon, the difference between standing in sunlight and standing in shadow is not a couple of degrees. It is hundreds of degrees. Shadow on the moon is not a cool spot. It is a thermal cliff. Step across the line where sunlight ends and shadow begins, and the ground temperature drops so fast and so far that the concept of shade takes on an entirely different meaning. This extends to some of the most fascinating and extreme places in the entire solar system. Near the moon's poles, there are craters so deep and so positioned that sunlight has never reached their floors. Not once. Not in 4 billion years. These permanently shadowed craters sit at temperatures estimated at roughly minus 240 degrees Celsius. That is colder than the surface of Pluto. That is among the coldest temperatures measured anywhere in the solar system. And these spots exist on a body only 240,000 miles from Earth, orbiting a world where you can walk outside in a t-shirt on a spring afternoon. The cold at the bottom of those craters is so extreme that it can trap water ice indefinitely, and molecules of water delivered by comet impacts or released from the lunar interior over billions of years, migrated across the surface, bouncing from spot to spot until they landed in one of these frozen traps from which they could never escape. The ice sits there in permanent darkness, preserved by cold so deep that the molecules lack the energy to break free and drift away. NASA's L-Cross mission confirmed the presence of this ice in 2009 by deliberately crashing a rocket stage into a permanently shadowed crater and analyzing the debris plume. Water was there, locked in the dark, held captive by cold that has persisted since before life existed on Earth. But here is what makes this truly strange. A thermometer floating just 1 meter above the sunlit lunar surface would read a completely different temperature than the ground below it. Not because the space 1 meter up is cold or warm in itself. The space has no temperature. The thermometer would be absorbing radiation from the sun directly and absorbing infrared radiation bouncing upward from the hot ground and simultaneously radiating its own heat outward into the void. Its reading would depend on its size, its color, how reflective it is, which direction it faces, and how far it sits from the surface. Change any single one of those properties and the reading changes entirely. The space itself has nothing to report. Only the objects within it have temperatures. Temperature is a property of matter. Where there is no matter, the concept dissolves. This is something we struggle to accept because we have never experienced it. Every moment of your life, you have been surrounded by matter. Air, water, solid ground. Your thermal experience has always been a conversation between your body and the substance around it. On the moon, there is no substance above the surface. The conversation ends. And what replaces it is a raw, unmediated relationship between object and radiation that produces results our Earth-trained minds find almost impossible to believe. Earth's atmosphere performs a thermal service so profound that we do not even notice it. It is like a heartbeat. You do not think about it. You do not appreciate it. It works every second of every day, as silently, invisibly, smoothing the savage radiation of a nearby star into the gentle warmth that lets rivers flow and forests grow and children play outside in the afternoon sun. Without it, Earth would be the moon, killing heat on one side, killing cold on the other, and no place in between where anything as fragile as a living cell could survive. The moon demonstrates something essential about the thermal nature of the universe. The gentle, moderate, livable temperature range we enjoy on Earth is not a natural consequence of being near a star. It is a consequence of having a specific kind of atmosphere wrapped around a specific kind of planet at a specific distance from a specific kind of star. Remove any one of those factors and the gentleness vanishes. What remains is the raw thermal reality of a universe where radiation rules absolutely and the difference between scorching and freezing is nothing more than which way you happen to be facing. And if the moon seems extreme, it is worth remembering that the moon is still close to the sun. It still receives strong solar radiation. It still sits within the warm inner region of our solar system. The thermal violence on its surface is a product of having no atmosphere, but it is at least warmed by a nearby star. The real question is what happens when you take that star away? What happens on the space station, on spacecraft venturing deeper into the solar system, when the problem is not managing the savage swing between sunlight and shadow, but managing heat in an environment where every watt must be carefully tracked, carefully balanced, carefully preserved, or rejected. That is a different kind of challenge entirely. And it reveals something about the cold of space that even the moon cannot fully teach us. Engineers who build spacecraft do not think about the temperature of space. That might sound strange after everything we have discussed, but it is true. They do not ask how cold is it out there, the way you might ask how cold it is before deciding whether to wear a jacket. Instead, they think about something called thermal balance. And this concept is the key to understanding why surviving in space is one of the hardest engineering problems humans have ever faced. Thermal balance works like this. Every spacecraft is simultaneously doing two things. It is absorbing energy from outside, and it is radiating energy away. Energy comes in from the sun as solar radiation. It comes in from nearby planets and moons as reflected sunlight and infrared glow. It even comes in from the faint cosmic microwave background, though that contribution is almost nothing. At the same time, the spacecraft radiates its own heat outward as infrared light, streaming energy into the void from every surface that faces the darkness. The spacecraft's temperature is determined entirely by the balance between these two flows. Energy in versus energy out. When the two are equal, the temperature holds steady. When more energy comes in than goes out, the spacecraft heats up. When more goes out than comes in, it cools down. There is no thermostat built into the universe. No automatic regulation. The spacecraft must manage this balance itself, or it dies. This might sound simple in principle. It is ferociously difficult in practice. Consider the International Space Station. It is the size of a football field. It orbits Earth at roughly 400 kilometers altitude, circling the planet every 90 minutes. Inside, 6 crew members live and work in a pressurized environment kept at a comfortable 22 degrees Celsius, shirt-sleeve weather. You could forget you were in space if not for the floating, but maintaining that comfortable temperature requires an engineering effort that most people never think about. The station's biggest thermal problem is not cold, it is heat. This surprises almost everyone. People assume that keeping warm is the challenge. It is not. Keeping cool is. Think about everything inside the station that produces heat. 6 human bodies, each generating about 100 watts of thermal energy just by being alive. More when exercising, dozens of computers running constantly, lighting panels, scientific experiments, communication equipment, power converters. Every electrical system produces waste heat as a byproduct of doing its job. All of this thermal energy accumulates inside a sealed metal container floating in a vacuum where there is no air to carry the heat away. No open window, no breeze, no convection to the outside world. If you sealed yourself inside a metal box on Earth with all those heat sources running and no ventilation, the temperature would climb until you could not survive. The same thing would happen on the space station without active cooling. The interior would get hotter and hotter until equipment failed and the crew was in serious danger. The station solves this problem with enormous radiator panels. If you have ever seen photographs of the station from the outside, you have seen them, though you might not have known what they were. They look like flat white panels extending outward from the main structure, spanning roughly 2,500 square feet of surface area. These radiators face away from the sun and emit infrared radiation into the cold void. They are the station's exhaust system, its only way to dump excess heat. Without them, the station would cook itself from the inside out. The cooling system works by circulating ammonia through pipes that collect heat from inside the station and carry it to the radiator panels, where the ammonia releases that heat as infrared radiation into space. It is elegant and essential. It runs constantly. It is monitored by flight controllers on the ground around the clock. If the system fails, the crew has hours, not days, to fix it before temperatures inside become dangerous. But the thermal challenge does not stop there, because while some parts of the station must be cooled, other parts must be heated. Components that spend extended periods in Earth's shadow, shielded from the sun, can get dangerously cold. Batteries must be kept above certain minimum temperatures or their chemistry stops working. Fuel lines can freeze solid. optical instruments can crack as their materials contract in the cold. Seals and gaskets can become brittle and lose their ability to hold pressure. So the station carries electric heaters as well, small devices scattered across its exterior structure that warm critical components during cold periods. The station is simultaneously running a cooling system to prevent overheating and a heating system to prevent freezing. Both systems operating at the same time on the same structure, managing thermal conditions that change every 45 minutes as the station passes from sunlight to shadow and back again. This is what thermal balance looks like in practice. It is not one problem. It is two opposite problems happening at once, on a structure where the sunlit side and the shadowed side can differ by 300 degrees, where the interior generates more heat than it can passively shed, and where individual components have narrow temperature ranges outside of which they stop working or break apart. Flight controllers in Houston and Moscow monitor thermal data from the station continuously. They adjust the station's orientation to control which surfaces face the sun. They activate and deactivate heaters based on orbital position. They watch coolant temperatures and radiator performance. Thermal management is not a background task. It is one of the primary concerns of every single day the station operates. A thermal system failure is treated with the same urgency as a depressurization alarm because the consequences can be equally severe. The deeper lesson here goes beyond engineering. The station's thermal battle reveals something fundamental about what the void actually is. Space is not an environment with a temperature you must survive. It is the absence of any environment at all. It provides nothing. No insulation, no buffering, no help of any kind. You bring everything with you, every watt of heating, every square meter of cooling, every layer of insulation, or you perish. The void does not participate in your survival. It simply allows physics to operate without interference, and physics in a vacuum is merciless. Every spacecraft ever launched has faced this same challenge in some form. The Apollo capsules that carried astronauts to the moon used a slow rotational maneuver called passive thermal control, sometimes informally called the barbecue roll, to keep the spacecraft evenly heated during the 3-day coast to the moon. Without this rotation, one side would bake in continuous sunlight, while the other side froze in shadow. By slowly spinning the spacecraft like a rotisserie chicken, engineers ensured that solar heating was distributed evenly around the hull, preventing dangerous thermal gradients from building up. The Voyager probes, now more than 14 billion miles from Earth, carry small plutonium-powered heaters to keep their instruments warm enough to function in the outer reaches of the solar system, where sunlight is so faint it provides almost no heating at all. Without those nuclear heat sources, the probes would have frozen solid decades ago. Their instruments would have cracked. Their electronics would have failed. The greatest journey of exploration in human history would have ended in silent cold somewhere past the orbit of Saturn. The James Webb Space Telescope takes the opposite approach. It needs to be cold, extremely cold. Its infrared detectors must operate at temperatures below 50 Kelvin, far colder than anything in the natural space environment near Earth. So Webb carries a tennis court-sized sunshield that blocks solar radiation from reaching its instruments, allowing them to cool by radiating their heat into the void. The same emptiness that threatens to freeze a space station's batteries is deliberately harnessed to chill a telescope's detectors to temperatures colder than anything found naturally for billions of miles in any direction. One spacecraft fights the cold, another embraces it. Both are responding to the same fundamental reality. The void does not care what you need. It does not care if you need warmth or cold. It offers neither. It simply allows radiation to flow unimpeded, and lets every object settle into whatever thermal state the physics dictates. The engineering exists to argue with that physics, to create local conditions that the universe would never produce on its own, and to maintain those conditions against the relentless, indifferent arithmetic of energy in versus energy out. And all of this, every heater, every radiator, every sun shield, every cooling loop, is ultimately fighting against or working with one number. One quiet, ancient, almost impossibly faint number that defines the thermal floor of the entire cosmos. A temperature set not by any star or planet, but by the oldest light in the universe. A glow so dim that no eye could ever see it, yet so perfectly everywhere that nothing in all of creation can escape its influence. That number is 2.725 Kelvin, and where it came from is one of the most extraordinary stories in the history of science. If you took an object, any object, a rock, a coin, a baseball, and placed it in the deepest, emptiest stretch of space you could find, far from any star, far from any galaxy, far from any source of warmth at all, and you simply left it there, something very specific would happen. The object would cool. Slowly, steadily, it would radiate its stored heat into the darkness, photon by photon, losing energy with every passing moment. Its temperature would drop, past the freezing point of water, past the freezing point of carbon dioxide, past the boiling point of liquid nitrogen, down and down through the temperature scale, falling toward a floor that it could approach but never quite reach on its own. And then it would stop, not at absolute zero, not at the coldest point physics allows. It would stop at 2.725 Kelvin, roughly minus 270 degrees Celsius, roughly minus 455 degrees Fahrenheit, just a breath above the lowest temperature the universe will ever permit, and it would stay there, indefinitely, balanced, still. The reason it stops is that something is shining on it, not a star, not a galaxy, not any object you could point to in the sky. What shines on it is the faintest, most ancient light in existence, a glow so dim that no human eye could ever detect it, no matter how long you stared, yet so perfectly uniform that it fills every cubic centimeter of the observable universe without exception. It arrives from every direction in the sky with almost exactly the same intensity, the same energy, the same whisper of warmth. It has no source you can locate by pointing. It comes from everywhere because it was made everywhere, nearly 14 billion years ago, when the universe was young and hot and glowing. This is the cosmic microwave background radiation, and it sets the temperature floor for everything in the cosmos. Here is what that means in practical terms. The object you left floating in deep space eventually reaches a point where the energy it absorbs from this ancient background glow exactly equals the energy it radiates away through its own thermal emission. Energy in matches energy out. The temperature holds steady. The object has reached thermal equilibrium with the universe itself, and the temperature at which that equilibrium occurs is 2.7 Kelvin. This number is the closest thing the universe has to a baseline temperature. It is not truly the temperature of space, because space is a vacuum, and a vacuum does not possess temperature in the strict scientific sense. It is the temperature that any object will eventually reach if left alone in the void with nothing else shining on it. The resting state, the default, the thermal bottom of the cosmos, and it is almost as cold as anything can ever be. Absolute zero, 0 Kelvin, is the theoretical point where all thermal motion stops. Atoms stop vibrating, molecules freeze in place. Energy reaches its lowest possible state. No physical process in nature has ever achieved absolute zero, The third law of thermodynamics tells us that reaching it precisely would require an infinite number of steps. It is a limit that can be approached but never touched. Even the most advanced laboratories on Earth, facilities that use laser cooling and magnetic traps to chill atoms to billionths of a degree above zero, cannot get all the way there. The universe itself cannot get there. But 2.7 Kelvin sits so close to that absolute boundary that the difference is almost meaningless on any human scale. On a thermometer that runs from absolute zero to the surface temperature of the Sun, roughly 5,800 Kelvin, the cosmic baseline would appear right at the bottom, indistinguishable from zero without a magnifying glass. To feel how extreme this is, consider some familiar cold benchmarks. Liquid nitrogen, the substance scientists use to flash freeze biological samples, boils at 77 Kelvin. The cosmic background temperature is roughly 29 times colder than liquid nitrogen. Liquid helium, the coldest commonly used cryogenic fluid on Earth, boils at 4.2 Kelvin. The universe's baseline temperature is colder even than liquid helium. The only way to reach 2.7 Kelvin in a laboratory is with specialized cryogenic equipment that costs millions of dollars and requires constant energy input to maintain. The universe reaches it effortlessly, passively, across almost its entire volume, simply by being empty. Now compare the cosmic floor to the coldest temperature ever recorded on Earth's surface. On July 21, 1983, the Soviet Vostok station in Antarctica measured minus 89.2 degrees Celsius. That translates to approximately 184 Kelvin. Brutal cold, lethal cold. The kind of cold that freezes exposed flesh in seconds and makes breathing feel like swallowing broken glass. The universe's background temperature is roughly 68 times colder than that Antarctic record. The coldest place any human has ever stood is practically warm compared to the thermal baseline of the cosmos. Our worst nightmare is the universe's normal condition, but 2.7 Kelvin is an average, a floor. It tells you what the universe defaults to when nothing interesting is happening nearby. And the universe is not uniform. It contains stars burning at millions of degrees in their cores, molecular clouds hovering at 10 or 20 Kelvin, accretion disks around black holes screaming past 1 billion degrees, glowing nebulae at thousands of degrees, planetary surfaces at every temperature in between. The thermal landscape of the cosmos is not a flat plane sitting at 2.7 Kelvin. It is a terrain of staggering extremes, towering peaks of unimaginable heat separated by vast frozen valleys that stretch for millions of light years in every direction. The question is not simply how cold space is. The question is how much of space sits at that killing cold versus how much of it is warm enough to matter. And the answer is where the real unease begins. Because the warm parts, the stars and planets and glowing clouds, are exceptions. Rare, scattered, isolated exceptions floating in an ocean of near absolute cold. The warmth is not the rule. The cold is the rule. It is the default condition of almost everything that exists. Imagine a dark ocean stretching from horizon to horizon in every direction. No shore, no bottom you can see, just water, black and still, extending further than your eyes can reach. Now scatter a handful of tiny candles across that ocean, each one floating on the surface, each one casting a small circle of light around itself. The candles are real. Their light is real. If you happen to be floating next to one, you can see and feel its warmth. But the ocean is vast and the candles are few, and anyone looking at the scene from a great distance would describe it as one thing and one thing only: dark. That is the thermal portrait of the universe. The candles are stars. The dark ocean is the 2.7 Kelvin void. And the void is winning, not by effort, not by force, but simply by being so much larger than everything else that the warmth barely registers as a statistical event. The cosmic microwave background also sets a hard limit on natural cold. No object anywhere in the universe, no matter how isolated, how shielded, how far from any star or galaxy, can cool below 2.7 Kelvin through natural processes alone. The background radiation bathes everything in a minimum energy input that prevents temperatures from falling any further. In laboratories on Earth, scientists have cooled atoms to billionths of a Kelvin using active technology. But those experiments require continuous energy input. The moment the machinery stops, the atoms warm back up. In the natural cosmos, without artificial help, 2.7 Kelvin is the basement, the absolute bottom, the coldest the universe will let anything become. This faint glow does two seemingly opposite things at the same time. It provides the last trace of warmth that prevents the cosmos from reaching absolute zero, and it defines the extreme cold that characterizes nearly everything in existence. It is both the universe's final source of universal warmth and the ruler that measures the depth of cosmic cold. Without it, space would be even colder, drifting toward true absolute zero with nothing to stop it. With it, space sits at 2.7 Kelvin, which sounds warmer than zero until you remember that it is colder than anything humans have ever experienced outside the most extreme research facilities ever built. But where did this number come from? The cosmic microwave background did not appear from nowhere. The universe was not always this cold. In fact, it was once unimaginably hot. The temperature has been falling since the moment of creation, and the story of that falling is the story of cosmic history itself. It begins nearly 14 billion years ago, in the first moments after the Big Bang, when every point in space burned hotter than the core of any star that has ever existed. And what happened to all that heat is one of the most remarkable transformations in the history of everything. Roughly 13.8 billion years ago, the universe did not exist. No space, no time, no matter, no energy in any form that current physics can describe. Then something happened. The event we call the Big Bang was not an explosion in space, the way a bomb goes off inside a room. It was an explosion of space. Space itself came into being and immediately began expanding, carrying with it densities and temperatures so extreme that nothing in modern experience comes close to matching them. In the first fraction of a second, everything that would eventually become every galaxy, every star, every planet, every ocean, and every living thing was compressed into a volume smaller than a single atom. The temperature in that primordial instant exceeded 10 trillion degrees. There is no way to make that number feel real. It has no human analog. It is a number that exists only in equations and in the first heartbeat of the cosmos. But it is where the story of cold begins, because from that moment forward, the universe has been cooling. Every second of every day for nearly 14 billion years. And it has never stopped. In the first second after the Big Bang, the temperature dropped from trillions of degrees to roughly 10 billion degrees. That sounds like a catastrophic plunge, and it was. But 10 billion degrees is still hotter than the core of the most massive stars burning today. The universe at 1 second old was a blinding storm of protons, neutrons, electrons, photons, and neutrinos, all smashing into each other with energies that would vaporize anything in the modern cosmos. Matter and radiation were locked together. Photons could not travel more than a tiny distance before slamming into a charged particle and bouncing off in a random direction. The universe was opaque, Light existed everywhere, but could go nowhere. Every direction was a wall of blazing fog. During the first 3 minutes, the temperature dropped below 1 billion degrees, cool enough for protons and neutrons to begin sticking together. Hydrogen nuclei formed naturally, since a hydrogen nucleus is just a single proton. Deuterium appeared when a proton and neutron joined. Helium nuclei assembled from 2 protons and 2 neutrons. Tiny amounts of lithium formed through slightly more complex combinations. This process, called Big Bang nucleosynthesis, lasted only a few minutes. By the time the universe was roughly 20 minutes old, the temperature had fallen too low for fusion to continue. The window shut. The cosmic forge closed. The ratio of hydrogen to helium was locked in at roughly 75% hydrogen and 25% helium by mass. A ratio that observations of the oldest stars confirm with striking precision billions of years later. But the universe was still extraordinarily hot. For hundreds of thousands of years after the Big Bang, temperatures stayed above 3,000 degrees. That is roughly the temperature of a blast furnace, and hot enough to keep all matter in a plasma state, where electrons roam freely rather than binding to atomic nuclei. Free electrons are extremely good at scattering photons. Every time a photon hit a free electron, it bounced off in a new direction. Light was trapped, bouncing through the plasma like a ball in a pinball machine with an infinite number of bumpers. No structure could be seen, no information could travel. The universe was a uniform, glowing, opaque haze stretching in every direction. Then, roughly 380,000 years after the Big Bang, the universe crossed a critical line. The temperature dropped below approximately 3,000 Kelvin. And something remarkable happened. Electrons finally slowed down enough to be captured by atomic nuclei. Protons grabbed electrons and became neutral hydrogen atoms. Helium nuclei captured their electrons too. For the first time in cosmic history, matter became electrically neutral. Scientists call this event recombination, though the name is a bit misleading since the electrons and nuclei had never been combined before. This was actually the first time atoms formed, ever. The consequences were immediate and dramatic. Neutral atoms do not scatter photons the way free electrons do. When the electrons disappeared into atoms, the universe suddenly became transparent. The photons that had been trapped for hundreds of thousands of years were released all at once, free to travel in straight lines across the cosmos for the first time. This moment is called the surface of last scattering. It represents the oldest light the universe will ever produce. Every photon released at that moment has been traveling through space ever since. They fill every cubic centimeter of the observable universe. They arrive at Earth from every direction in the sky. They have been streaming through the cosmos for nearly 13.8 billion years. This is the cosmic microwave background. But those photons do not arrive in the same form they were released. When they left the surface of last scattering, they were visible light, a deep, dull, orange-red glow at roughly 3,000 Kelvin. If you could have been present at that moment and somehow survived, the entire sky in every direction would have glowed a dim red. No darkness anywhere, no shadows, no contrast. Just a uniform glow extending to infinity. Since that moment, the universe has expanded by a factor of roughly 1100. Space itself has stretched, and every photon traveling through it has been stretched along with it. This is not a metaphor. The actual wavelength of each photon has physically increased as space expanded. Longer wavelengths mean lower energy. Lower energy means lower temperature. Think of it like this. Imagine drawing a wave on a rubber band and then pulling the rubber band from both ends. The wave stretches. The peaks get farther apart. the wave becomes longer. That is what the expansion of space does to every photon traveling through it. The light that was once visible, once orange-red and glowing, has been stretched so far over billions of years that it now exists as microwaves. Its wavelength has grown from less than a micrometer to over a millimeter. Its effective temperature has dropped from 3000 Kelvin to just 2.725 Kelvin. The entire sky still glows, just as it did at recombination. But the glow has shifted so far into the microwave part of the spectrum that no eye, no biological eye anywhere in the universe could ever detect it. You are bathed in it right now. It passes through the walls around you. It fills the room you are sitting in. It fills every room, or every building, every forest, every ocean, every corner of the cosmos. And you cannot see it, cannot feel it, cannot sense it in any way without purpose-built instruments. The cosmic microwave background is the afterglow of creation, dimmed and stretched by the expansion of space itself until it became invisible to everything except machines specifically designed to detect it. The fire that once blazed at trillions of degrees, that filled every point in the universe with blinding energy, now whispers at 2.7 Kelvin. Still there, still everywhere, but so faint that humanity needed its most sensitive instruments to even notice it existed. And the cooling is not over. The universe continues to expand. As it does, the cosmic microwave background continues to stretch and cool. Every day, the background temperature drops by an amount so small that no current instrument could measure the change. But the trend is real and relentless. In the far future, billions of years from now, the temperature will be lower. A universe twice its current size will have a background temperature of roughly 1.4 Kelvin. A universe 10 times larger will glow at just 0.3 Kelvin. The afterglow is slowly fading. The ember is dying. The Big Bang deposited an enormous quantity of thermal energy into a tiny volume. That energy has been spreading out as space expands, thinning across an ever-growing cosmic volume like a drop of ink dissolving in an ocean that never stops growing. The density of thermal energy decreases with expansion. Temperature drops. What was once a searing plasma capable of preventing atoms from forming is now a whisper of microwave radiation, so faint it took the most advanced instruments ever built to detect it. The universe spent its thermal inheritance in the first few 100,000 years and has been running on fumes ever since. The 2.7 Kelvin we measure today is not a number that was chosen or set. It is the exhausted remnant of a once blazing cosmos, the leftover warmth of a fire that has been dying for nearly 14 billion years, and the story of how we found that remnant, how two engineers stumbled onto the oldest light in the universe while trying to fix an antenna in New Jersey, is one of the greatest accidental discoveries in the history of human knowledge. In 1964, two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, were trying to build a better antenna. They were not looking for the origins of the universe. They were not hunting for ancient light or cosmic secrets. They were communications engineers working on satellite technology, and they had a problem. Their antenna, a large horn-shaped instrument originally built for early satellite communication experiments, was picking up a faint, persistent hiss that they could not explain. And it was driving them crazy. Arno Penzias and Robert Wilson were meticulous scientists. They wanted their antenna to be as clean and sensitive as possible, which meant eliminating every source of unwanted noise. They calibrated their equipment carefully. They accounted for radio interference from nearby New York City. They pointed the antenna away from known astronomical sources. They checked every cable, every connection, every component for faults. Nothing worked. The hiss remained. They even climbed inside the horn of the antenna and scraped out pigeon droppings. A pair of pigeons had been nesting inside the horn, and Penzias and Wilson suspected the birds might be contributing thermal noise to their signal. They trapped the pigeons, drove them to a release site far away, cleaned out the droppings, and tested again. The pigeons flew back. They removed them again. They cleaned the antenna again. They tested again. The hiss was still there. It came from every direction, equally. It did not change with the time of day. It did not change with the season. It did not change when they pointed the antenna at different parts of the sky. It was perfectly uniform, perfectly constant, and perfectly inexplicable by any source on Earth they could identify. The signal corresponded to a thermal source at roughly 3.5 Kelvin, just a few degrees above absolute zero. Penzias and Wilson spent months trying to figure out what they had found. They wrote it up as an unexplained excess antenna temperature, a technical description that dramatically understated what they were actually looking at. Because the answer to their puzzle was not sitting in their antenna. It was sitting in an office at Princeton University, just 40 miles away. Robert Dick, Jim Peebles, and their colleagues at Princeton had independently predicted that if the Big Bang theory was correct, the universe should be filled with a faint thermal radiation left over from its hot early phase. They had worked out the physics. They knew roughly what temperature this radiation should have. And they were in the process of building their own antenna to search for it when they received a phone call from Penzias and Wilson describing their mysterious noise. The realization was immediate and electrifying. The persistent hiss in the Bell Labs antenna was not instrument noise. It was not pigeon droppings. It was not radio interference from human activity. It was the remnant heat of the Big Bang itself. The oldest light in the universe. He released when the cosmos was just 380,000 years old, arriving at a radio antenna in New Jersey after a journey spanning nearly the entire history of time. Penzias and Wilson had stumbled onto the most important cosmological discovery since Edwin Hubble proved the universe was expanding. They received the Nobel Prize in Physics in 1978. The pigeons did not receive any recognition. The initial measurement was rough by modern standards. Penzias and Wilson determined the temperature to be approximately 3.5 Kelvin with significant uncertainty. But the discovery opened a floodgate. Over the following decades, scientists built increasingly powerful instruments to study this ancient glow with greater and greater precision. And what they found transformed our understanding of the universe more profoundly than almost any other observation in the history of science. The first major leap came with the Cosmic Background Explorer satellite, known as COBE. Launched by NASA in 1989, COBE carried instruments designed specifically to measure the cosmic microwave background from above Earth's atmosphere. This mattered because Earth's atmosphere absorbs and emits microwaves on its own, contaminating ground-based measurements. A satellite eliminates that problem entirely. COBE produced two groundbreaking results. First, it measured the spectrum of the cosmic microwave background and found that it matched the theoretical prediction for a perfect blackbody radiator with extraordinary precision. A blackbody is an idealized object that absorbs all incoming radiation and emits energy in a very specific pattern determined entirely by its temperature. The spectrum COBE measured fit the theoretical curve so perfectly that the data points were indistinguishable from the predicted line. When the COBE team presented this result at a scientific conference, the audience gave a standing ovation. It was the most perfect blackbody spectrum ever measured in nature. The temperature was pinned down to 2.725 Kelvin with an uncertainty of less than 1,000th of a degree. But COBE's second result was even more important. The satellite detected tiny temperature variations in the cosmic microwave background. The radiation was not perfectly uniform. Some directions in the sky were a few 100,000ths of a degree warmer than average. Others were a few 100,000ths cooler. These variations were minuscule, roughly 1 part in 100,000, but their existence was revolutionary. These tiny warm and cool spots were not random imperfections. They were the fingerprints of the earliest structures in the universe. Regions that were slightly warmer at the time of recombination were also slightly denser. Those denser regions had marginally stronger gravitational pull. Over billions of years, that tiny gravitational advantage attracted surrounding matter, growing denser and denser until galaxies, galaxy clusters, and the entire cosmic web condensed out of the initial smoothness. The warm spots in the cosmic microwave background are the seeds from which every galaxy in the observable universe eventually grew, including ours. After COBE, 2 more satellite missions pushed the measurements further. The Wilkinson Microwave Anisotropy Probe, known as WMAP, launched in 2001. It mapped the cosmic microwave background with roughly 35 times the angular resolution of COBE, revealing detailed patterns in the temperature fluctuations that COBE could only glimpse. WMAP determined the age of the universe to be 13.77 billion years. It confirmed that ordinary matter, the atoms that make up stars, planets, and people, makes up only about 4.6% of the total content of the cosmos. Dark matter accounts for roughly 23%, and dark energy, the mysterious force accelerating the expansion of the universe, makes up the remaining 72%. All of these numbers, extracted from patterns in ancient microwave radiation, from the faint afterglow of a universe that was once a wall of blazing fog. The cosmic microwave background became the Rosetta Stone of cosmology. Nearly everything we know about the large-scale properties of the universe comes from studying this faint cold glow. The European Space Agency's Planck satellite, launched in 2009, refined the picture even further. Planck observed the cosmic microwave background at 9 different frequency bands with sensitivity and angular resolution that surpassed WMAP by another significant factor. The resulting maps are the most detailed images of the early universe ever produced. Planck refined the age of the universe to 13.798 billion years. It confirmed the background temperature at 2.725 Kelvin. And it revealed subtle patterns in the fluctuations that constrain theories about what happened during the first trillionth of a second after the Big Bang. 3 satellite missions spanning 2 decades transformed a mysterious antenna hiss into the single most informative observation in all of cosmology. Yet a noise that annoyed 2 engineers in New Jersey became humanity's deepest look into its own origins. And here is what all of it means for the question we started with. The 2.7 Kelvin baseline is not just a number, it is a fossil, a thermal relic of a moment when the universe was young and hot and glowing. Every photon in the cosmic microwave background has been traveling since recombination, carrying a tiny packet of energy from an era when the cosmos was 3,000 degrees everywhere. Those photons have lost almost all their energy to the expansion of space. They have been stretched, diluted, and cooled from incandescent visible light to invisible microwaves over 13.8 billion years, the 2.7. Kelvin we measure today is the exhausted remnant of a once blazing universe, and the cooling is not finished. It will never be finished. As long as space continues to expand, the background will continue to cool. The afterglow of the Big Bang is a dying ember, slowly fading toward a darkness that will never quite become absolute, but will approach it across timescales that make the current age of the universe look like a passing afternoon. But the cosmic microwave background tells only half the thermal story. It describes what happens in the absence of local energy sources. It tells you the temperature of the void, the empty stretches between galaxies where nothing shines and nothing burns. The universe, however, is not entirely empty, and scattered through the cosmic darkness are objects of extraordinary thermal violence. Stars that burn at millions of degrees, accretion disks that reach temperatures rivaling the first moments after the Big Bang. The question now becomes how those scorching exceptions compare to the freezing rule. How much of the universe actually burns, and how much sits in the cold dark? The answer, when the numbers are laid bare, is far more lopsided than anyone expects. Stars are the exceptions that prove the rule. In a universe that defaults to 2.7 Kelvin, stars are pockets of thermal defiance, so extreme they seem almost absurd. Our Sun maintains a surface temperature of roughly 5,500 degrees Celsius. Its core reaches 15 million degrees. These numbers exist on a completely different scale from the cold that surrounds them, separated from the cosmic baseline by factors of millions. A star is not just warm. It is a sustained thermonuclear explosion held together by gravity and powered by the fusion of hydrogen into helium at pressures and temperatures that have no parallel anywhere else in nature. Every star you see in the night sky is performing this same violent act. The Sun converts roughly 4 million tons of matter into pure energy every single second. Not 4 million tons of fuel burned into ash the way wood burns in a fireplace. 4 million tons of mass annihilated, transformed into photons through Einstein's famous equation relating energy to mass. That energy radiates outward in every direction, crossing 93 million miles of vacuum to reach Earth in about 8 minutes. It warms our planet. It drives our weather. It powers photosynthesis. It sustains every living thing on the surface of this world. And our Sun is not even impressive by stellar standards. It is a middle-aged, medium-sized yellow dwarf, unremarkable among the hundreds of billions of stars burning throughout the Milky Way. Larger stars burn far hotter. Blue supergiants like Rigel in the constellation, Orion blaze with surface temperatures exceeding 11,000 degrees Celsius, roughly twice the temperature of our Sun. Their cores can reach hundreds of millions of degrees, fusing not just hydrogen, but helium, carbon, oxygen, and progressively heavier elements in nested shells of nuclear fire. The most massive stars known to science, monsters weighing over 100 times the mass of the Sun, burn through their fuel with such ferocity that their entire lives span only a few million years. Compare that to our Sun's expected 10 billion year lifespan. These stellar giants live fast, burn outrageously hot, and die in explosions that briefly outshine entire galaxies. On the opposite end, red dwarfs burn cool and slow. Their surface temperatures hover around 3,000 degrees Celsius, dim compared to the Sun, but still 1,000 times hotter than the cosmic background. Red dwarfs are the most common type of star in the universe. Roughly 70% of all stars in the Milky Way are red dwarfs. They are so dim that not a single one is visible to the naked eye from Earth, despite being the most numerous objects in the stellar census. They burn their fuel so sparingly that their lifespans stretch into the trillions of years, far longer than the current age of the universe. Every red dwarf that has ever ignited is still burning today. Not one has died. These dim, patient furnaces will be the last sources of stellar warmth the universe ever knows. But stars are not the only sources of extreme heat. When matter falls toward a black hole, it does not drop in quietly. It spirals inward through a swirling disk of gas and dust called an accretion disk, compressed by gravitational forces so intense that the material heats to temperatures rivaling the early universe. Around supermassive black holes, the kind lurking at the centers of galaxies, accretion disk temperatures can climb into the hundreds of millions of degrees. The most extreme environments found in active galactic nuclei and quasars produce temperatures approaching 1 billion degrees or more. These are among the hottest sustained temperatures in the modern universe. Supernova explosions create momentary extremes that dwarf everything else. When a massive star exhausts its fuel, its core collapses in a fraction of a second. The iron core, roughly the mass of our Sun, compressed into a sphere the size of a city, implodes at speeds approaching a quarter of the speed of light. The temperature at the collapsing core reaches roughly 100 billion degrees for a brief, violent instant. That is hotter than any stable star, hotter than any accretion disk, hotter than the universe has been at any point since its first second of existence. A dying star briefly recreates conditions from when the cosmos was less than 1 second old. The explosion that follows can outshine every other star in the host galaxy combined for weeks, releasing more energy in a few seconds than the Sun will produce over its entire 10 billion year lifetime. And then it fades. The heat disperses. The expanding remnant cools over thousands of years, eventually blending into the cold interstellar medium. The thermal violence is spectacular but brief. A match struck in a dark room that lights up everything for an instant before the darkness returns. All of these objects, from red dwarfs to quasars, from stellar nurseries to supernova remnants, create local thermal environments that deviate wildly from the 2.7 Kelvin background. Some by factors of billions. They are real, they are powerful, they are spectacular, and they are tiny. Yet this is the fact that transforms the temperature question from a matter of physics into something close to existential vertigo. The hot objects are vanishingly small compared to the space between them. Consider the Sun. You could fit roughly 1.3 million Earths inside it. Its diameter spans about 865,000 miles. It dominates our local environment so completely that its gravity holds planets in orbit billions of miles away. But the nearest star, Proxima Centauri, sits 4.25 light-years away. That is roughly 25 trillion miles. If you shrank the Sun to the size of a ping-pong ball, Proxima Centauri would be another ping-pong ball, sitting roughly 720 miles away. Between those two tiny spheres lies nothing. 720 miles of empty tabletop. 2 specks of warmth separated by a wasteland that dwarfs them by a factor of roughly 30 million. This is the standard arrangement. It is how stars are spaced throughout our galactic neighborhood. Some regions pack stars more tightly, but even in the densest parts of the Milky Way, stars remain separated by distances vastly larger than themselves. Now, consider the numbers at cosmic scale. The observable universe has a radius of approximately 46.5 billion light-years. Its total volume is roughly 4.2 times 10 to the 80th power cubic meters. The total volume of all stars in the observable universe are estimated at roughly 10 to the 24th power stars, each somewhat smaller than the Sun, comes to approximately 10 to the 51st power cubic meters. Divide stellar volume by total cosmic volume, and you get a fraction on the order of 10 to the negative 29th power. Let me translate that. The hot interiors of stars occupy less than 1 billionth of 1 billionth of 1 billionth of the total volume of space. Write out the zeros if you want. It starts with a decimal point, followed by 28 zeros, and then a 1. That is how much of the universe is filled with stellar fire. The rest, everything else, is vacuum sitting at or near the cosmic microwave background temperature. Warm matter is not rare. It is essentially non-existent when measured as a fraction of cosmic volume. If you could somehow paint every warm object in the universe bright red and every cold region blue, and then zoom out far enough to see the whole cosmos at once, you would see blue. Nothing but blue. The red dots would be there, scattered throughout like individual atoms in an ocean. But they would be so small and so widely separated that no eye could pick them out against the overwhelming blue of the cold. The universe is not a place where hot and cold compete on roughly equal terms. It is a place where cold has already won, totally, completely, across essentially all of space. The hot objects that fill our sky with light, that sustain life on Earth, that power the chemistry of every habitable world, account for a share of cosmic volume so small that rounding it to zero would not meaningfully change any calculation in cosmology. Stars are brilliant. Stars are essential for the existence of anyone capable of asking questions about temperature. But they are thermal afterthoughts. The main product of cosmic evolution is not stars. It is empty, cold, silent vacuum. Stars are a side effect, a glorious one, but a side effect. And the architecture of the universe at its largest scales drives this point even further. Because when you zoom out past individual stars, past galaxies, past galaxy clusters, the cosmos reveals its true structure. A structure dominated not by the bright filaments where matter collects, but by the vast, dark, empty voids between them. Voids where nothing burns, where nothing shines, where the temperature story is simple and absolute and has been unchanged for billions of years. Galaxies are not scattered evenly through space like stars sprinkled across a dark cloth. They are organized. They follow a pattern so vast and so strange that it took decades of careful observation to reveal it. When astronomers mapped the positions of millions of galaxies across enormous volumes of space, using surveys like the Sloan Digital Sky Survey, what emerged was a structure that resembles something surprisingly familiar. Foam. The kind of foam you see when you blow bubbles in soapy water. Thin walls surrounding empty spaces. Except this foam is made of galaxies, and the empty spaces are measured in hundreds of millions of light years. Scientists call this the cosmic web. Galaxies cluster along vast filaments and walls, long strands of matter stretching across the universe like threads in an impossibly large spider web. Where filaments intersect, galaxy clusters form. Dense knots containing thousands of galaxies bound together by gravity. These clusters are the cities of the cosmos, the places where matter concentrates most heavily and where the most dramatic astrophysical events occur. But between the filaments lie cosmic voids, and voids are the true dominant feature of the universe. A typical cosmic void spans 100 to 300 million light-years across. The largest known voids exceed 1 billion light-years in diameter. To feel the weight of those numbers, remember that our entire Milky Way galaxy is roughly 100,000 light-years wide. A modest cosmic void could contain thousands of Milky Ways laid end-to-end across its diameter. And inside that void, you would find almost nothing. The Buta's void, one of the first supervoids ever discovered, stretches roughly 330 million light-years across. Inside it, astronomers have found fewer than 60 galaxies. To appreciate how empty that is, consider that our local group of galaxies contains over 50 galaxies packed into a region just 10 million light-years across. The Buta's void is 33 times wider and contains roughly the same number of galaxies. If Earth sat at the center of the Buta's void instead of in the Milky Way, astronomers would not have discovered external galaxies until far more powerful telescopes existed. The night sky beyond our own galaxy's stars would have been almost perfectly black. Inside these voids, the density of matter drops to roughly 10 to 20% of the cosmic average. A few lonely dwarf galaxies drift through the emptiness, but they are so rare and so widely separated that you could travel for tens of millions of light years in any direction without encountering a single one. No galaxy clusters form in voids. No rich populations of stars exist. No supernovae explode with any meaningful frequency. The thermal environment approaches the pure cosmic microwave background temperature with almost no local energy sources to raise it even slightly. Scientists estimate that cosmic voids occupy approximately 80 to 90% of the total volume of the observable universe. The filaments, walls, clusters, and galaxies where stars actually burn crowd into the remaining 10 to 20%. Think about what that means. If you closed your eyes and teleported to a truly random point anywhere in the observable universe, the overwhelming probability is that you would appear inside a void, far from any galaxy, far from any star, surrounded by nothing but the 2.7 Kelvin glow of the cosmic microwave background stretching to the horizon in every direction. You would be floating in a region colder than almost anything on Earth, darker than any night sky visible from our planet's surface, emptier than the best vacuum chamber ever built by human hands. And you would stay that way for as long as you drifted, because the nearest galaxy might be 100 million light years away in any direction you chose to travel. Even within the filaments where galaxies concentrate, most of the volume remains cold. Galaxies themselves are mostly empty space. The Milky Way's stellar disk is thin and sparse. Stars occupy a vanishingly tiny fraction of galactic volume. The gas and dust between stars, called the interstellar medium, sits at temperatures ranging from roughly 50 to 10,000 Kelvin depending on its state. But this material is spread so thin, typically just a few atoms per cubic centimeter, that its thermal contribution to the surrounding volume is negligible. If you drew a straight line through the Milky Way in any random direction, you would pass through light years of near vacuum for every fraction of a second you spent inside the atmosphere of a star. A galaxy is not a warm object. It is a collection of warm specks embedded in a cold matrix. And the specks are outnumbered by the matrix in a way that defies easy description. Imagine a gymnasium. Now imagine placing a single grain of sand somewhere on the floor. That grain of sand, relative to the volume of the gymnasium, gives you a rough sense of how a star relates to the space around it inside a galaxy. Now imagine millions of gymnasiums connected end to end, each one containing its own single grain of sand. That is closer to the true picture. The grains are real. The warmth they produce is real. But the defining characteristic of the scene is the empty space between them. Between galaxy clusters, thin strands of gas thread through the cosmic web along filaments. Some of this gas is surprisingly hot in a technical sense, reaching temperatures of 100,000 to 10 million Kelvin, heated by gravitational shocks during the process of structure formation. This warm-hot intergalactic medium contains a significant fraction of all ordinary matter in the universe, perhaps as much as 40 to 50% of all baryons. But the word hot here is misleading. Temperature measures the average speed of particles. Density measures how many particles there are. A gas can have extremely high temperature and extremely low density at the same time. And when density is very low, no high temperature means almost nothing in practical terms. A cubic meter of this intergalactic gas might contain only a handful of particles. Each particle moves fast, which gives the gas a high temperature reading. but there are so few of them that the total thermal energy in that cubic meter is almost zero. If you stood inside this gas, you would feel nothing. No warmth whatsoever. Your body would still radiate heat into the void and receive almost nothing in return, regardless of whether the surrounding particles happened to be moving at speeds corresponding to 1,000,000 degrees. A room full of ordinary air at 20 degrees Celsius contains astronomically more thermal energy than a cubic light year of intergalactic plasma at 10 million degrees. The intergalactic medium is hot in name only. In practice, it warms nothing. This distinction between temperature and thermal energy is essential. Temperature tells you how fast particles are moving. Thermal energy tells you how much total heat is actually present. A single particle moving at 1,000,000 degree velocity carries an almost unmeasurably tiny amount of actual energy. A trillion slow-moving particles at room temperature carry far more. The intergalactic medium has temperature without meaningful thermal energy. It is like saying a room is noisy because a single mosquito is buzzing very fast. Technically true, practically irrelevant. This is why the universe can contain stars at millions of degrees, accretion disks at billions of degrees, and intergalactic gas at millions of degrees, yet remain overwhelmingly, dominatingly cold. The hot stuff is either too small or too sparse to matter at cosmic scales. The cold vacuum wins not because it is powerful, but because it is everywhere. It does not need to defeat warmth. It simply needs to exist in vastly greater quantity. And it does, by a margin so extreme that all the heat in all the stars in all the galaxies amounts to a rounding error in the thermal ledger of the cosmos. The cosmic web itself illustrates this with striking clarity. Look at those maps of galaxy distribution. The bright parts, where galaxies trace out the scaffolding of the web, occupy a thin minority of total volume. The dark parts, the voids, dominate overwhelmingly. Filaments are cobwebs strung across cathedral-sized spaces of darkness. Galaxy clusters are small knots where a few threads happen to cross, and the vast interiors of the voids stretch on and on for hundreds of millions of light years with nothing but the fading afterglow of creation to fill them. It is a map of loneliness drawn at the largest scale imaginable. Within those voids, the temperature story is simple and unchanging. Nothing heats them except the cosmic microwave background. The void sits at 2.7 Kelvin. Decade after decade, century after century, eon after eon. Unchanging and undisturbed across timescales that make the age of Earth look like a heartbeat. The cold in these regions is not temporary. It is not seasonal. It is not the kind of cold that ends when the sun rises, because no sun will ever rise there. It is the permanent cold of a universe whose original heat has been stretched and diluted beyond recovery. The voids were never warm after the first few 100,000 years of cosmic history. They will never be warm again. They represent the natural resting state of a cosmos that was hot for a brief moment after its birth and has been cooling ever since. The thermal portrait of the universe is not a balanced landscape of hot and cold competing for dominance. It is a portrait of almost total, overwhelming cold, interrupted by pinpoints of heat so rare and so small that they barely register at cosmic scales. And the question that remains is not just about space, it is about time. Because even the pinpoints of heat, the stars, the glowing nebulae, the burning accretion disks, are temporary. They have expiration dates written into the physics of their existence. And when those dates arrive, the cold does not just win across space, it wins across time as well, permanently, irreversibly. And on a timeline so long, it makes the current age of the universe seem like the opening frame of a film that runs for eternity. Everything we have explored so far has been about space, about how much of the universe is cold right now and how little of it is warm. But there is another dimension to this story that makes the picture even more stark. Time. Because the warm objects in the universe, the stars, the glowing clouds, the burning disks around black holes, are not permanent features of the cosmos. They are temporary. Every one of them has an expiration date. And when you measure the age of warmth against the age of cold, the proportions become so lopsided that the human mind struggles to hold them. Stars have been burning for roughly 13.5 billion years. The first generation ignited from primordial hydrogen a few hundred million years after the Big Bang, lighting up a universe that had been dark since recombination. Stars have been forming and dying ever since, each generation seeding the next with heavier elements forged in their cores. Our Sun is a third-generation star, built from the ashes of ancestors that lived and died billions of years before our solar system formed. The cycle of stellar birth and death has been running for most of cosmic history. It feels permanent. It feels like it will go on forever. It will not. The supply of hydrogen available for nuclear fusion is finite. It is being consumed in stellar cores across every galaxy in the observable universe, and no known physical process will ever replenish it. New stars still ignite every year. In the Milky Way alone, the roughly 3 solar masses worth of material collapses and catches fire annually. But the rate of star formation has been declining since its peak roughly 10 billion years ago. The universe is past its prime. The golden age of stellar ignition is already behind us. Each passing billion years sees fewer new stars born than the billion years before. The massive stars will go first. They always do. A star 50 times the mass of the Sun burns through its fuel in just a few million years and explodes as a supernova. The Sun-like stars last longer, roughly 10 billion years each, but they too will eventually exhaust their hydrogen, swell into red giants, and shed their outer layers, leaving behind dense white dwarf cores that produce no new energy. Red dwarfs will be the last to go. These tiny, dim stars are the most frugal consumers of hydrogen in the universe. Their internal structure fully mixes their fuel, allowing them to burn through nearly their entire mass, rather than just the core. The smallest red dwarfs will burn steadily for perhaps 10 to 15 trillion years before exhausting their supply. That is roughly 1,000 times the current age of the universe. Long after every massive star has exploded and every sun-like star has become a white dwarf, the red dwarfs will still be glowing. Dimly, quietly, alone in the growing darkness. But even they will eventually run out. And when the last red dwarf sputters and fades, no new stars will ignite. The raw material will have been consumed or scattered beyond recovery. The universe will go dark. What follows is almost impossible to describe in human terms because it unfolds across timescales that make all of recorded history, all of human evolution, all of Earth's existence feel like less than a blink. After the last star dies, the universe enters what physicists call the degenerate era. The cosmos will be populated by the cooling remnants of dead stars. White dwarfs, those compressed cores left behind when sun-like stars exhaust their fuel, will cool slowly over trillions of years. They begin their afterlives glowing with residual heat, some initially hotter than the surfaces of the most massive living stars, but they produce no new energy. They are embers, not fires. Over timescales measured in quadrillions of years, they will fade from dim yellow to deep red to infrared to microwave, and finally settle into a temperature indistinguishable from the cosmic background. Each cooling white dwarf is a tiny replay of the universe's own thermal history, born hot, fading slowly, approaching but never quite reaching absolute cold. Neutron stars will undergo a similar fade, radiating away their enormous rotational and thermal energy over comparable timescales. They will spin down, cool off, and eventually become dark, silent objects drifting through empty space with nothing to distinguish them from any other cold lump of matter. Black holes will be the last significant objects remaining, and their fate is the strangest of all. Through a process called Hawking radiation, predicted by physicist Stephen Hawking in 1974, black holes slowly lose mass by emitting faint radiation from their event horizons. The process is unimaginably slow. A stellar mass black hole, one formed from the collapse of a single massive star, takes roughly 10 to the 67th power years to evaporate completely. That is a 1 followed by 67 zeros, a number so large that writing it out in full would fill a page. A supermassive black hole, the kind sitting at the center of a galaxy, weighing millions or billions of times the mass of the Sun, takes roughly 10 to the 100th power years. A 1 followed by 100 zeros. This number is called a googol. The evaporation time for the largest black holes exceeds a googol years. There is no human experience, yet no metaphor, no comparison that can make this duration feel real. It is simply beyond the reach of intuition. When the final black hole evaporates in a faint burst of radiation, the universe will contain nothing but diffuse particles and photons drifting apart in an expanding void that grows colder with every passing moment. Now here is the part that changes everything. When measured against this cosmic timeline, the era of starlight is a brief flicker. The stelliferous era, the period during which stars exist and shine, spans roughly 100 trillion years at most. That sounds enormous, and by human standards it is. But the eras that follow, the long cooling of white dwarfs, the slow evaporation of black holes, extend across timescales so much longer that the stellar era shrinks to almost nothing. If you represented the entire future history of the universe as a single calendar year, with the Big Bang on January 1st and the evaporation of the last black hole on December 31st, the entire era of starlight, all 100 trillion years of it, would occupy the first fraction of a millionth of a second after midnight on January 1st. The rest of the year, every month, every week, every day, every hour, every remaining second, would pass in total darkness at temperatures approaching absolute zero. Let that sink in. Every star that has ever burned, every sunrise, every warm ocean, every photosynthetic leaf, every campfire, every candle, every moment of warmth in the entire history of the cosmos. All of it fits into a sliver of time so thin it would be invisible on any calendar you could draw. The age of warmth is not just brief, it is so brief compared to the cold future that calling it brief is itself a dramatic understatement. The universe will spend the overwhelming majority of its existence in total darkness and total cold. Stars are a temporary phenomenon. The warmth they provide is a temporary gift. The habitable zones they create are temporary shelters against an eternal cold that will eventually reclaim everything. Every living thing that has ever existed on Earth, or on any other world in any galaxy, exists during this narrow window when the universe still produces light and heat. Before the first stars, there was only cooling radiation approaching the background temperature. After the last stars, there will be only cooling remnants fading toward absolute zero across durations so vast they make the current age of the universe seem like the blink of an eye. The warm present is sandwiched between a cold past and a colder future. A thin, bright line drawn across an infinite dark page. Earth itself is temporary. The Sun has roughly 5 billion years of stable burning remaining. But long before it dies, its gradually increasing brightness will make Earth uninhabitable. In roughly 1 billion years, solar output will have increased by about 10%, enough to trigger a runaway greenhouse effect that boils the oceans. The warmth that sustained life for 4 billion years will become the heat that destroys it. Even the Sun's gift comes with an expiration date. Against this backdrop, the existence of warmth anywhere in the universe takes on a weight that physics alone cannot fully carry. We are not just warm. We are warm during the only era when warmth is possible. We are warm on a planet whose warmth depends on conditions so specific and so temporary that their existence feels less like an inevitability and more like something that deserves to be noticed, carefully, gratefully. Before the window closes and the cold, patient and infinite settles in for good, gather everything we have traveled through and hold it together in your mind for a moment. The universe began in unimaginable heat. It has been cooling for 13.8 billion years. The expansion of space stretched the primordial fire into a faint microwave whisper. At 2.7 Kelvin, barely above the coldest condition physics allows. Stars burn as local exceptions, furious but tiny, scattered across distances so vast that the space between them is permanently cold. Cosmic voids spanning hundreds of millions of light years sit at the baseline temperature with nothing to warm them. The fraction of cosmic volume occupied by stellar interiors is so small it vanishes into the noise, and the fraction warm enough for liquid water, for chemistry, for anything resembling the conditions that sustain life, is smaller still. So small that expressing it requires stacking negatives upon negatives until the number loses all connection to anything a human mind can picture. Now, it is time to say what that truth actually means. The terrifying truth is not that space is cold. That much is obvious to anyone who has ever looked at a clear night sky and felt the ancient chill of distance. The terrifying truth is that warmth is rare, staggeringly, absurdly, almost impossibly rare. The warm, habitable conditions we experience every day on the surface of this planet represent a cosmic anomaly so extreme that the universe, if it could be said to have a normal setting, would not recognize our environment as anything other than a freak occurrence. We live in a thermal outlier, a pocket of warmth so improbable against the backdrop of cosmic cold that its existence demands not just explanation, but something approaching wonder. Think about what is required for Earth to be warm. We need a star, not just any star. A star of the right mass, burning at the right rate, emitting the right kind of radiation to heat a rocky planet without destroying it. The Sun has done this with remarkable stability for 4.5 billion years. A star 10% more massive would burn hotter and die sooner, possibly before complex life had time to evolve. A star 20% less massive would emit mostly infrared radiation, changing the chemistry of any atmosphere it warmed. But the star is only the beginning. Earth must orbit at precisely the right distance. A few percent closer and the oceans boil. A few percent farther and they freeze. The habitable zone, the orbital sweet spot where liquid water can persist on a rocky surface, is so narrow compared to the solar system that it occupies less volume than the gap between Jupiter and Saturn. Earth threads this needle with a precision that looks, from a cosmic perspective, almost unreasonable. Even within the habitable zone, distance from the star is not enough. Earth needs an atmosphere. Without one, the surface would swing between brutal extremes with every rotation, baking in sunlight and freezing in shadow, just like the moon. The greenhouse effect, driven by water vapor and carbon dioxide, raises Earth's average surface temperature from -18 degrees to approximately 15 degrees Celsius. A swing of 33 degrees that makes the difference between a frozen rock and a living world. The atmosphere itself depends on Earth's mass being large enough to hold gas against the erosion of solar wind, but not so large that it captured a thick hydrogen-helium envelope like Jupiter. Earth's magnetic field, generated by convection currents in a liquid iron core, must be strong enough to shield the atmosphere from being stripped away by charged particles from the Sun. Mars lost much of its atmosphere through exactly this process. Its magnetic field faded as its core cooled. Mars was probably warm once. It is not warm now. Layer these requirements together and a picture emerges. The right star, the right orbit, the right mass, the right atmosphere, the right magnetic field, the right geological activity to cycle carbon and regulate temperature over billions of years, the right amount of water, the right kind of moon to stabilize the planet's axial tilt. Possibly even the right arrangement of giant planets in the outer solar system to deflect incoming debris that would otherwise bombard the inner planets with sterilizing frequency. Each requirement is the product of a chain of events stretching back to the formation of the solar system, to the supernova that seeded our molecular cloud with heavy elements, to the stellar generations that preceded our Sun, to the galaxy formation process, to the density fluctuations in the early universe that seeded the galaxy in the first place. The chain extends across the entire history of cosmic evolution. Pull any single link out and the rest collapses. The warmth you feel right now is the end product of that chain, stretching backward through 4 billion years of planetary history, 5 billion years of stellar evolution, and 13.8 billion years of cosmic expansion. None of it was guaranteed. Physics did not mandate a warm Earth. The equations that govern the universe are completely indifferent to whether any particular rock orbiting any particular star happens to fall within a temperature range compatible with life. Now, scale outward. Earth is one warm world orbiting one stable star among hundreds of billions of stars in one galaxy among trillions of galaxies. How many of those stars host planets with the right mass, the right atmosphere, the right magnetic field, the right geological history to sustain warmth over billions of years? We do not know. The Kepler mission suggested that roughly 1 in 5 Sun-like stars may host a rocky planet in the habitable zone. That would yield billions of candidates in the Milky Way alone. But sitting in the habitable zone is only the first filter. A planet can occupy the correct orbital distance and still be a frozen wasteland without an atmosphere, or a scorching hellscape if its greenhouse effect runs away, or a barren rock if it has no magnetic field. Each additional filter eliminates candidates. Each requirement makes the final count smaller. The James Webb Space Telescope is beginning to analyze exoplanet atmospheres, searching for chemical signatures that might indicate habitable conditions. Within the coming decades, we may have our first evidence of whether any nearby worlds are warm in the way that matters. But even the most optimistic estimates place truly habitable planets at a tiny fraction of all planetary systems. And even those are only candidates. The vast majority may fail tests we have not yet learned to apply. The warm places where life might exist represent a share of cosmic volume that rounds to zero by any reasonable standard. This is not a flaw in the universe. It is a direct consequence of how physics works at cosmic scales. Gravity pulls matter into clumps. Fusion ignites those clumps into stars. Radiation warms narrow bands around those stars, but gravity operates on a tiny fraction of cosmic matter. Most matter sits in diffuse halos of dark material that will never form stars. Most ordinary matter that collects into galaxies sits in gas too thin to collapse, and even the matter that does become stars heats only the thinnest possible shell of surrounding space before its influence fades into the background. The universe is, in the most literal physical sense, a machine for producing cold, not by design, not with intent. It simply follows laws that, when applied to the actual distribution of matter and energy across cosmic volumes and cosmic timescales, inevitably produce a cosmos where warmth is the exception and cold is everything else. The title of this story promised a terrifying truth. Here it is. The cold does not surround us the way darkness surrounds a campfire, with the fire holding its own against the night. The cold is the night. It is everything. And our warmth, the warmth of Earth, the warmth of life, the warmth of consciousness, contemplating its own improbability, is a single candle burning in a darkness that stretches farther than light has traveled since the beginning of time. That candle is real. Its flame is genuine. But the darkness around it is bigger than any mind can hold, and the candle will not burn forever. But it is burning now, here, on this world, in this moment, and you are part of its light. The room around you is quiet now. The numbers have been spoken. The distances have been walked. The temperatures have been felt as deeply as language allows. And now the journey slows, the way all long journeys do, settling into stillness, the way a river slows as it nears the sea. You are lying somewhere safe, somewhere warm. Your body is held by gravity against the surface of a planet that orbits a steady, middle-aged star at precisely the right distance to keep water liquid and air breathable and skin comfortable against the cool of evening. The blanket over you traps infrared radiation from your own body, the same radiation that streams into the void from every object in the cosmos. Except here, it stays close. Here, it is kept. Here it wraps around you like the atmosphere wraps around the earth, holding warmth in place against the endless cold beyond. Your breath deepens. Your thoughts soften. The universe is vast and cold and ancient beyond reckoning. But this room is small and warm and yours. And that, against all the odds the cosmos could stack, is enough. Rest now. The stars will keep burning while you sleep.